Alright, welcome to another video on op-amps, and in this video we're going to be talking about the non-inverting amplifier. So the non-inverting amplifier, which is essentially just running like this, is a variant of the inverting amplifier in the sense that it does not actually invert the direction of the signal, so it doesn't actually flip it around as we saw in the previous example, but rather retains the same kind of directionality. So if your input voltage is coming in like this, suppose it's a sinusoidal voltage, it is coming in like that, then essentially what you're going to get out is something that has changed in amplitude but essentially retains the same phase. Whereas with the inverting amplifier, you will normally notice a 90-degree out of phase kind of output voltage. And that's the main difference, and this is the configuration that we use. So what we're going to do is we're going to find an expression for V out in terms of V in. That's usually what we want of an amplifier. We want to find out an expression for V out in terms of the input voltage. Now, first thing we notice is that the input voltage is essentially coming in the positive terminal. Now, we know by the ideal amplifier rules that there's no current coming in. So any current in this case, I plus should be equal to 0. Assume ideal operation. Now the next thing we know is that the difference between the two terminals in terms of potential should be 0. So the potential over here should be equal to the potential over here. So essentially this is also going to be V in, which means the potential at this node over here is going to be V in. Now this is connected to ground over here. We have two resistors. And if we look at just this little section over here, so let's look at it from right to left. What we notice is that this is the same kind of configuration as you would have for a voltage divider. Now, we spent a few videos explaining what voltage dividers are and how they work. So if we actually remember the original equation for that, we should be able to find out exactly what this is. But let's assume that we have forgotten what the voltage divider kind of equation is. We're going to find out what it is. So first thing I'm going to do is I'm going to assume that there is some current coming in over here. So we have a potential difference. This is the top potential. The potential over here is 0. So essentially we have some current coming in from this side. It's going to flow like this. So we want to find an expression for that current. Now that current is going to be equal to the difference in potential, which is going to be V0 minus 0. So it is going from V0 to 0. And that's going to be divided by the total resistance, which is R1 plus R2. And that's going to give us V0 divided by R1 plus R2. Now the next thing we're going to do is we want to find out exactly how does this compare to the input voltage. Okay, so we want to find out the potential over here. So to do that, we're going to calculate the potential drop across R1, which is going to be equal to I times R1, and that's going to be R1 and then R1 plus R2 times V0. Now V in is going to be equal to V0 minus the potential drop across resistor 1, which is going to be equal to V0 1 plus R1 over R1 plus R2. Okay. And then the next thing is, well, we're going to basically find an expression for V0 in terms of V in. So to do that, all we're going to do is we're going to say, okay, V0 times, we're going to have R1 over here. So that's 2R1 plus R2 divided by R1 plus R2 is going to be equal to V in. And so, actually, I've made a mistake here. I'm very sorry about this. So it should have been minus over here. So let me just rectify that very quickly. This should have been minus. I don't know why I added the two together. So it's this minus that. So it should be a minus over here. That's why the expression didn't make a lot of sense. So that means that R1 is going to disappear with R1. So it's gonna be, we're going to be left with essentially just R2 at the top. And then we're going to have R1 plus R2. Okay, so that's going to be our expression over here, and then that's going to be equal to V in, and that means that V naught is going to be equal to R1 plus R2 divided by R2 times V in. In other words, what we could do is we could essentially split this off into two fractions, and we could say that V naught is going to be equal to 1, so that's R2 over R2 is 1, and then plus R1 over R2 V in, which means that the gain of a non-inverting amplifier is going to be given by 1 plus R1 over R2. Of course, assuming that the configuration is given by R1 and R2 in this fashion. So that means we can control the gain by using that ratio, and of course there's gonna be this 1 added to it, but if you're looking at things like kilo ohms, adding a 1 it's definitely gonna change your answer, but you have to be aware of the fact that, you know, it's just going to be some sort of gain into it. So it is going to be slightly different. I mean, it's very hard to get a non-inverting amplifier that doesn't have this extra 1, but this is the general kind of non-inverting amplifier you will find. It's quite useful for when you want to essentially amplify a signal without inverting it or changing the phase of that. And we're going to see how this applies in different situations, but at least this gives you a better idea of how to analyze op-amp circuits and how we can use those basic ideal op-amp rules to derive these expressions.